Swayam Prabha. Digital India. Educated India.
I welcome you all to the next lecture, lecture number 7. Actually, the first 6 lectures, the contents are from the module number 1, and from this lecture, for the next 6 or 7 lectures, it will be the contents would be from module number 2 in the subject Thermodynamics and Thermal Engineering. Let us have a quick recap what we have discussed in the entire module number 1. So we have discussed about the history of thermodynamics, what are the types of systems, open system, closed system, isolated system, examples, and steady flow energy equation, application of steady flow energy equation, then the laws of thermodynamics, the zeroth law of thermodynamics, the first law of thermodynamics for system undergoing a cycle, for system undergoing a change of state, that is a process. Then we have studied about 2 statements pertaining to second law of thermodynamics, Kelvin-Planck statement and Clausius statement. In Kelvin-Planck statement, we have seen how the heat engine is producing work, executing its task, and in case of a Clausius statement, refrigerator and heat pump working between a source and a sink, and the COP of the refrigerator and the heat pump were also evaluated. We have seen the concept of entropy, Clausius inequality in the first module. Now let us see the second module. To begin with, in lecture number 7, we will be seeing one air standard cycle. Primarily this module 2 focuses on various air standard cycles. So the contents of my presentation are actual comparison between actual and air standard cycle, the PV diagram and TS diagram of Otto cycle. So this is the Otto cycle, air standard, which we will be studying efficiency and a numerical question as well. What are all the various processes in an Otto cycle, derivation of thermal efficiency for an Otto cycle, and one numerical question covering the various aspects of Otto cycle. Before I explain the difference between the actual and the air standard cycle, what is this Otto cycle? It is an ideal air standard cycle. It is an ideal cycle on which a petrol engine works. This is similar to the conventional process which takes place in a petrol engine. All of us are familiar with the working principle of a spark ignition engine, which is the petrol engine. There are 4 strokes involved: suction stroke, compression stroke, power stroke or expansion stroke, and exhaust stroke. What happens in the suction stroke is the air fuel mixture is admitted inside the cylinder, and the piston moves from TDC to BDC during that process. So the intake is admitted inside the cylinder through the suction valve or the inlet valve. After the air fuel mixture is admitted, then the piston starts moving from BDC, bottom dead center, to top dead center, where the air fuel mixture is compressed to high pressure and high temperature. At the end of compression stroke, the ignition takes place. Ignition and the combustion of the air fuel mixture takes place, which pushes the piston again down from top dead center to bottom dead center. So that indicates the expansion stroke or power stroke. The power is produced by the engine, or the power output from the engine is there. Then we have the exhaust gases which are there, which have built up inside the cylinder, so which has to be sent out, discharged to the atmosphere through the exhaust valve. And again, by the time this process is completed, the next set of air fuel mixture for the next cycle would commence. So this is the conventional process which is taking place in a spark ignition engine. Let us see how this air standard cycle, ideal cycle, deviates or differs from the actual cycle. If you see the actual cycle, the working fluid, that is the air fuel mixture, it does not behave like an ideal gas. Whereas in case of an ideal cycle, the air standard cycle, which we are going to analyze, the working fluid behaves as an ideal gas. Yesterday we have seen in one of the lecture, that is lecture number 6, where we have seen what is an ideal gas, what is the equation of state. There are three forms of equations of state: PV equal to MRT, P into small v, that is specific volume, equal to RT. Then there is one more form of this one in terms of number of moles, equation of state in terms of number of moles. We have seen what is the difference between R and R bar. R is characteristic gas constant. For air it is 0.287 kilojoule per kg Kelvin, and R bar is the universal gas constant, 8.314 kilojoule per kg mole Kelvin. So the working fluid, when we say the working fluid behaves as an ideal gas, it obeys the gas law PV equal to MRT perfectly. Not only that one, the specific heat, when we say a working fluid is behaving as ideal gas, the specific heat Cp value is specific heat, it remains constant. It has a fixed value, it does not vary. The second difference is the working fluid is not circulated in the open cycle. If you take the conventional spark ignition engine, that is a petrol engine, what happens during the suction stroke, the air fuel mixture is admitted, air petrol mixture is admitted inside the cylinder, and in the fourth stroke, that is the exhaust stroke, after the engine produces the power in the third, at the end of the third stroke, that is the power stroke, the exhaust gases are discharged or sent out from the cylinder to the atmosphere through the exhaust valve, So this process takes place as the piston pushes the gases from bottom dead center to top dead center. So at one process the air fuel mixture is taken inside, whereas on the after it has converted into useful work, the exhaust gases are discharged let out into the atmosphere. So the working fluid is in one way it is not circulated again, it is not reused again and again. So that is what I have mentioned in the point number 2. Working fluid is not circulated again, it is like an open cycle, not a closed cycle. The cycle, the working fluid does not follow a perfect thermodynamic cycle in this case. Whereas in case of an ideal cycle, which is the air standard cycle, the working fluid is circulated again, so it is like a closed cycle. Point number 3, in the actual cycle the specific heat varies because the working fluid does not behave like an ideal gas, whereas in the ideal cycle, air standard cycle, specific heat is constant. Fourth one is, in the actual cycle, the combustion process which takes place at the end of compression stroke, and before the beginning of power stroke, that is ignition and combustion. So that combustion process is replaced by a heat addition process. So that is one major difference between the actual cycle and the ideal cycle. Similarly, the exhaust process which takes place in the exhaust stroke, it is replaced by a heat rejection process in a ideal cycle, And last one is, in the actual cycle the processes are not internally irreversible, whereas in the ideal cycle the processes are internally reversible. Now what is the need for going for a air standard cycle or analysis of an ideal cycle? If you see the actual cycle, sometimes the analysis, when we want to do the detailed analysis, the modeling analysis, it becomes a little bit tedious one, complicated one. So to make the analysis simpler, these assumptions have been made. What are all the assumptions that have been made? Point number 1 is, the working fluid behaves like an ideal gas, number 1. Second one is, the specific heat remains constant, it does not vary with the temperature. Third one is, the combustion process is replaced by either a constant volume or constant pressure process that varies from one cycle to another cycle, which we will see in today's lecture. Combustion process is replaced by heat addition process. Exhaust stroke or exhaust process is replaced by a heat rejection process. And the fifth difference is, the process which are occurring in the ideal cycle are internally reversible. So this is the pressure volume and temperature entropy diagram of an Otto cycle. So I have drawn, like I have said before, most of the thermodynamic cycle have 4 processes. And if you see the arrow mark, the direction in which the arrow is marked in this cycle, so it is like a clockwise direction. It is in the clockwise direction. If you take any thermodynamic cycle, a power producing cycle, the arrow marks of a power producing cycle will be in the clockwise direction, Whereas if a thermodynamic cycle has an arrow mark in the anti-clockwise direction, it is a refrigeration cycle. It is a power absorbing cycle. So let me explain the process one by one as I draw the PV diagram and the TS diagram separately so that you can understand easily. So let me draw the PV diagram, this one. This is pressure, this is volume. Let me plot the TS diagram also simultaneously. Temperature, entropy. Now the process 1 to 2 is isentropic compression. Isentropic compression 1 to 2. The volume decreases from V1 to V2, pressure increases from P1 to P2. How to represent an isentropic compression on a TS diagram? Isentropic means reversible adiabatic process, entropy is constant. Entropy is constant. So this is the increase in temperature from T1 to T2 and pressure increases from P1 to P2. P1 and this is the volume. This is the volume V2 after compression. Let me mark this point here so that we can mark the dotted line, and this is the volume before compression. So as the piston moves from BDC to DC, the volume swept by the piston decreases, the pressure of the exerted on the working fluid increases. So air is considered as the working fluid throughout the cycle in case of air standard cycle. So this is isentropic compression. Next, so this is process 1 to 2. So that's what I have written here. 1 to 2 is isentropic compression. Second one is, little ago I was told that the combustion process is replaced by a heat addition process. Heat addition process. So in an Otto cycle, heat addition takes place at constant volume. Constant volume. So this is 2 to 3. So this is how you have to represent a process on a TS diagram, constant volume. So during this process, the amount of heat supplied is Qs. Amount of heat supplied is Qs. So this is Qs. So process 2 to 3 is constant volume heat addition. Because the heat is added at constant volume, the Otto cycle is sometimes referred to as constant volume cycle. Because the heat is added at constant volume, the Otto cycle is also called as constant volume cycle. So 2 to 3 is constant volume. This is point number 3. So during the heat addition, we can see the pressure increases from P1, P2 to P3, P2 to P3, and temperature increases from T2 to T3. T2 to T3. So now the power stroke is this one. So that is isentropic expansion. Isentropic expansion. So this is 1 to 2 is isentropic compression. So 3 to 4 also will be similar to the curve 1 to 2, but the direction will be opposite. But the direction will be, so this is isentropic expansion, and this here x axis is entropy and y axis is temperature. So any isentropic line will be perpendicular to x axis. So this is 3 to 4. And so 3 to 4 is isentropic expansion, just opposite to process 1 to 2, isentropic compression. And process 4 to 1 is constant volume heat rejection, constant volume heat rejection, QR. And here process 4 to 1 will be similar to process 2 to 3, because 2 to 3 is constant volume heat addition, 4 to 1 is constant volume heat rejection. Only the direction of the arrow will be, so I will draw like this. So during this process 4 to 1, the heat is rejected. The amount of heat rejected, I am denoting it as QR. the amount of heat supplied that is during the heat addition process is Qs and Qr. So, here that completes the cycle, and again the air will be compressed isentropically from state point 1 to 2, then heat addition will be there at constant volume, then isentropic expansion followed by constant volume heat rejection, If you see these, this is what I have plotted here, 1 to 2, 2 to 3, 3 to 4, 4 to 1, and during the process 2 to 3 and 4 to 1 heat is added as well as heat is rejected respectively. If you see this one, so this is the clearance volume, this portion is the clearance volume in the cylinder, and this is the, that is V2 equal to clearance volume, and this is the swept volume. Let us explain what is clearance volume and swept volume. Clearance volume is a volume which is provided at in the cylinder, so that when the piston is moving from the forwards from the BDC to TDC, so if you do not provide clearance, it will directly hit on the walls of the cylinder. So, there are chances that the life of the cylinder will go down, there will be more wear and tear. So, a small amount of volume is provided. So, volume of the cylinder above the piston when the piston is at TDC, volume of the cylinder above the piston when the piston is at TDC. So, let me explain with the diagram. Suppose if this is the cylinder and this is the piston which has the piston and the connecting rod. Suppose this is TDC position, this is BDC. TDC refers to the position above which the piston cannot be moved. Similarly, BDC refers to the position below which the piston cannot be moved in the downward direction. So, this will be the stroke volume or the swept volume, that is volume swept by the piston between TDC and BDC, and the little volume which is provided, that will be the clearance volume. This is the clearance volume. Okay. So, suppose let us take this one. The valves, inlet valve will be placed here, the exhaust valve will be, this is the cylinder head, So, let us take this volume as the clearance volume. This is the cylinder head, the valve, inlet valve, exhaust valve, in case of petrol engine, spark plug, all these things are placed on the cylinder head. So, when the piston is at TDC, the volume of the cylinder above the piston is referred to as clearance volume, and the volume swept by the piston between TDC and BDC or BDC and TDC, it is called the stroke volume. Clearance volume plus swept volume is equal to total volume, So, the total volume of the cylinder is the summation of clearance volume and swept volume. The other name for swept volume is stroke volume. So, here the same thing I have shown on the pressure volume diagram. This portion is the clearance volume, that is V2 is equal to V3, because 2 to 3 is a constant volume process, and similarly V1 is equal to V4, So, here if you see V2 is equal to V3, which is nothing but the clearance volume, and this 1 to 2, that is this is the swept volume, the total volume is V1, this is the total volume which is V1. So, the total volume is the summation of clearance volume and swept volume. So, this basics you should remember. So, to summarize, there are 4 processes in Otto cycle. 1 to 2 is isentropic compression, 2 to 3 is constant volume heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection process. If you have a look at the PV diagram and TS diagram, the maximum pressure that has occurred in the cycle is at point number 3. This is the point of maximum pressure, So, the maximum pressure is P3, and the maximum temperature is also attained at point number 3, the corresponding on the TS diagram. So, this is the maximum
temperature. So, the maximum temperature reached in the cycle is
at state point number 3, at state point number 3. This is obviously due to the heat addition process. The heat addition process commences at state point number 2 and it ends at state point number 3. So, the pressure and the temperature is peak at its state point number 3. With this background, let us derive the thermal efficiency of the cycle. Let us derive the thermal efficiency of the cycle. So, because in module 2 there are 4 air standard cycles which we will be studying. All these 4 air standard cycles involve efficiency, derivation of efficiency. So, I will do it at a little bit faster rate within the lecture period itself. So, efficiency is output by input, output by input. Okay. I have taken in all the air standard cycles, QS is the amount of heat supplied, QS is the amount of heat supplied and QR is the amount of heat rejected. So, output is nothing but like net work done. We have seen in the heat engine, it takes QH amount of heat and reject QL amount of heat. The difference between QH and QL is the net work done by the engine. So, similarly, I am supplying QS amount of heat, QR amount of heat is rejected. So, the difference is the net output of the or work done by the engine in the thermodynamic cycle divided by heat input is heat supplied. So, divide this term QS by QS is equal to 1, the second term is QR by QS. Okay. Now, let us substitute the formula. Heat supplied is in Otto cycle, heat supplied and heat rejected takes place at constant volume. For a unit mass of air, that is 1 kg. So, QS it is supplied at constant volume. So, mCV delta T. So, CV into delta T. What is delta T? Delta T, if you see the process 2 to 3, 2 to 3 is constant volume heat addition. So, 2 to 3 constant volume heat addition is T3 minus T2, T3 minus T2. So, this is the process T3 minus T2, that is the delta T for constant volume heat addition. So, CV into T3 minus T2, mCV delta T, I have taken m as 1 kg of air and QR is equal to, again heat rejection is also at constant volume, CV into delta T, CV into T4 minus T1. T4 is higher temperature, 4 to 1 is the constant rejection process. So, the highest temperature is T4 and T1 is lower temperature. So, T4 minus T1, heat rejection is at constant volume. So, that is why I put CV here. If it is constant volume, you have to put CV. If it is constant pressure, we have to mention Cp. So, this is substitute these two here. So, let us take 1, 2, 3, substitute 2 and 3, substitute 2 and 3 in 1. So, thermal efficiency is equal to 1 minus, instead of QR I will substitute CV into T4 minus T1, instead of QS I will substitute CV into T3 minus T2, T3 minus T2. So, CV and CV will get cancelled, you will get 1 minus T4 minus T1 divided by T3 minus T2. Here I have expressed the thermal efficiency or the air standard efficiency in terms of temperature T1, T2, T3 and T4. So, let this be equation number 4. Now, I will simplify this equation and I will derive the thermal efficiency of the air standard cycle. So, this is what I have got here. You can see here equation number 4, 1 minus T4 minus T1 divided by T3 minus T2. So, detailed steps are given here and I am also writing when I am doing the derivation so that students can understand easily. You can either refer this writing notes on the PPT or already the typed equations in the PPT. Now, I am going to define one term, that is compression ratio. Compression ratio is represented by the letter compression ratio R. Okay, so V1 by V2, V1 by V2. What is V1 by V2? If you see, V1 is the volume before compression, V1 is the volume before compression and V2 is the volume after compression, V1 by V2. So, this is the compression ratio V1 by V2, whereas V1 is equal to V4 and V2 can be written as V3. V1 is equal to V4 because 4 to 1 is constant volume process and V2 is equal to V3. Similarly, 2 to 3 is constant volume process. So, now let us consider the process 1 to 2. Process 1 to 2. Let us consider the process 1 to 2. 1 to 2 is isentropic compression process. So, let us refer the PV and TS diagram. See, 1 to 2 is isentropic compression, 1 to 2 is isentropic compression, entropy is constant. So, where the pressure and temperature of the working fluid, which is air, increases. Okay. So, let us write the relation, thermodynamic relation between temperature and volume for an isentropic process. Isentropic process is nothing but reversible adiabatic process. So, T2 by T1 is equal to, okay, T2 by T1 is equal to, okay, let me write it here itself, V1 by V2 whole power gamma minus 1. See, this is derived from the basic equation for a reversible adiabatic process. In one of the lecture, I have explained that the equation is PV power gamma is equal to constant, PV power gamma equal to constant. So, for state 1 you can write P1 V1 power gamma, P2 V2 power gamma, replace P1 and P2 using the ideal gas equation, equation of state PV equal to MRT. So, after simplification you will get this term, T2 by T1 is equal to V1 by V2 whole power gamma minus 1. If it is T2, here it will be V1 1, if it is 1, here it will be 2 for the temperature volume relation. But we know that V1 by V2 is equal to R, which is the compression ratio. Therefore, T2 by T1 is equal to R power gamma minus 1. From this we can write T2 value as in terms of T1 and compression ratio gamma minus 1. So, T2, so let this be, here I have expressed T2 in terms of T1. So, let this be equation number 5 because the previous, this is equation number 4, this will be equation number 5. Now, if you see this equation number 4, there are 4 temperatures T1, T2, T3 and T4, T1, T2, T3 and T4. Now, I have expressed T2 in terms of T1. Next, I will take the process 3 to 4, either I will express T4 in terms of T3 or T3 in terms of T4, and when we do that one, the simplification becomes easier. We will get the thermal efficiency or the air standard efficiency of the Otto cycle in terms of gamma and R, that is compression ratio and index of compression. That is, gamma is the ratio of Cp by Cv, Cp by Cv. So, consider the process 3 to 4. So, first I consider the process 1 to 2, which is isentropic compression. Next, I am going to consider the process 3 to 4. 3 to 4 is isentropic expansion process, isentropic expansion process. We should remember that whenever you write a relation using gamma, the process it should be a reversible adiabatic or an isentropic process. This gamma equation, suppose if I try to write a similar equation for process 2 to 3, that means it is not correct, because 2 to 3 is constant volume process. Similarly, 4 to 1 is constant volume heat rejection process. 2 to 3 is a heat addition process at constant volume. So, for a constant volume process or a constant pressure process, one should not write an equation involving gamma. Gamma, when you write T2 by T1 equal to P2 by P1 whole power gamma minus 1 by gamma, or T2 by T1 equal to V1 by V2 whole power gamma minus 1, or a volume and pressure relation in terms of gamma, that means the process should be a reversible adiabatic process. So, such an equation involving gamma is applicable only for reversible adiabatic process, reversible adiabatic process. Of course, if gamma is replaced by n, it becomes a polytropic process. So, this type of equations cannot be written for a isobaric process or a isochoric process. So, that should be kept in the mind. Now, let us consider the process 3 to 4. Okay. Process 3 to 4 is isentropic expansion. Isentropic expansion. This is compression, this is expansion. So, I will write the relation between T3 by T4. See, you can write, we can write T4 by T3 also. Similarly, here also you can write T1 and T2. So, the final answer is not going to change. Interchanging these terms does not affect the final answer. So, T3 by T4, if it is T3 I will write V4, if it is T4 I will write V3 whole power gamma minus 1. In both these thermodynamic equations I have written the relation between temperature and volume, because I know the volume ratio V1 by V2 is the compression ratio, V1 by V2. V1 is the total volume, V2 is the clearance volume, V2 is the clearance volume. So, now T3 by T4 is equal to V4 by V3. Have a look at the pressure volume diagram. What is V4? V4 is V1, V4 is V1 and V2 is V3. So, that I am going to substitute here. V4 is equal to V1 and okay. V4 is V1 and V3 is equal to V2. Since V4 is equal to V1 and V3 equal to V2, as process 2 to 3 and 4 to 1 are constant volume process. So, that is the reason. So, V1 by V2. So, replace V4 by V1 and V3 by V2 whole power gamma minus 1. Now, V1 by V2, that ratio is compression ratio. So, this is equal to R power gamma minus 1. So, left hand side we have got T3 by T4. From this you can find T3 equal to T4 into R power gamma minus 1. So, that is what I have found here. Okay. T3 equal to T4 into compression ratio to the power of gamma minus 1. So, that will be equation number 6. Equation number 6. Substitute 5 and 6 in 4. Substitute 5 and 6 in 4. Substitute 5 and 6 in equation number 4. Therefore, thermal efficiency is equal to 1 minus numerator, there is no change, because I have expressed T2 in terms of T1 and T3 in terms of T4. So, in the denominator of this equation number 4 only I will be substituting. There is no change in the numerator term. 1 minus T4 minus T1 divided by, instead of T3 I will substitute equation number 6, T4 power T4 into R power gamma minus 1 minus T2. T2 is T1 into R power gamma minus 1.
So, R power gamma minus 1 can be taken as a common term in the denominator. So, this is equal to 1 minus numerator, there is no change, R power gamma minus 1, and inside the bracket we will have T4 minus T1. So, these two terms will get cancelled. So, the final equation is thermal efficient Otto cycle is 1 minus 1 by R power gamma minus 1. So, this is the thermal efficiency or the air standard efficiency of an Otto cycle. This is the thermal efficiency or the air standard efficiency of an Otto cycle. So, if you see this one, this equation, the thermal efficiency of an Otto cycle is a function of compression ratio R and gamma, that is ratio of the specific heat at constant pressure to constant volume. So, this is with this the derivation, the thermal efficiency of the Otto cycle has been done. Now, let us solve one numerical problem based on this Otto cycle. An ideal Otto cycle has a compression ratio of 8. So, the R value is given. At the beginning of compression process, air is at 1 bar and 17 degrees centigrade. 800 kilojoules per kg of heat is transferred to the air during the heat addition process. Determine the pressure, temperature and volume at various states in the cycle, net work output, thermal efficiency and mean effective pressure. This mean effective pressure is a term which is a fictitious term. It is the pressure which would be acting, if acting on the cylinder, would produce the same amount of work that is produced during the actual cycle. So, that is the mean effective pressure. So, let us write the given data. So, here it is clearly given at the beginning of compression, means compression starts at state point 1 and ends at state point 2 So, beginning of compression is the condition of the air, that is pressure and temperature at state point 1 is given. So, P1 is 1 bar and T1 is 17 degrees centigrade. So, let me solve this problem. P1 is equal to 1 bar, T1 is equal to 17 degrees centigrade, converted into Kelvin. So, convert this temperature into Kelvin. So, you will get at 273, 290 Kelvin. Compression ratio is given as 8. So, small letter alphabet R is used to express the compression ratio. So, R is given. There is one more data which is given in the problem. 800 kilojoules per kg of air supplied of heat is transferred to the air. That is the amount of heat supplied during the process is given. Heat supplied is represented by the letter Qs. So, Qs is also given 800 kilojoules per kg. So, let us draw the PV diagram so that it is easy to refer, and this one, at least this one, though it is already there. So, this is the PV diagram: pressure, volume, isentropic compression, constant volume heat addition, isentropic expansion, and so this is 1, this is 2, constant volume heat addition, 2 to 3, 3 to 4 is expansion. So, this is the amount of heat added and this is the amount of heat rejected. So, V1 equal to V4, here V2 is equal to V3. So, these two are applicable. Okay, so what is the first question? We have to find out the pressure, temperature and volume at various state points in the cycle. That means we know the pressure and temperature at 1. So, we do not know the pressure and the temperature at state point 2, 3 and 4. So, that we have to find out, and also the volume. So, it is a quite lengthier problem. Okay, we will try to finish it in this lecture. So, now consider the process 1 to 2. 1 to 2 is isentropic compression. So, we can write the relation between temperature and volume, because we know the compression ratio is V1 by V2. So, we know V1, V2, we know temperature T1 is given. So, we can easily find temperature T2 by writing the correlation between temperature and volume. Okay. So, the same correlation which I used during the derivation T2 by T1, consider the process 1 to 2, 1 to 2. T2 by T1 is equal to V1 by V2 whole power gamma minus 1. Gamma is taken as 1.4, the standard value, unless otherwise it is mentioned, it is always 1.4 for air, 1.4 for air, because the Cp of air is constant 1.005 kilojoule per kg Kelvin, Cv of air is constant 0.717 kilojoule per kg Kelvin. So, when you divide 1.005 divided by this one, you will get gamma value. Difference between Cp and Cv will give characteristic gas constant, ratio between Cp and Cv will give gamma. So, that should be very clear. So, now this V1 by V2 is nothing but R power gamma minus 1. So, from this we can find T2 is equal to T1 into R power gamma minus 1. So, gamma is equal to 1.4, gamma is equal to 1.4 for air, and the working fluid which we are considering in the air standard cycle throughout the cycle is air. So, now T1 is given, it should be substituted in Kelvin, R is given, compression ratio, gamma is 1.4 known. So, we can find out the temperature too at the end of compression. So, let me draw the TS diagram also here. 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So, this is 2 to 3 is heat addition, this is temperature, this is entropy, and 4 to 1 is heat rejection. 4 to 1 is heat rejection. Okay. So, now I am going to find out the temperature at this point. I am going to find T2. So, using this one, substitute the values T1, R and gamma. Okay. So, let us see the answer. T2 is equal to 664 Kelvin, 664 Kelvin, 664 Kelvin. So, the temperature after compression is 664, the temperature before compression is 290 Kelvin. So, the temperature has increased from 290 to 664. Okay. Now, similarly we can write the thermodynamic relation between pressure and volume, that is P2 by P1 equal to V1 by V2 whole power gamma. Similarly, for the process 1 to 2, because I have to find out the pressure at state point 2, So, P2 by P1 is equal to, this relation I will be using, V1 by V2 whole power gamma, V1 by V2 whole power gamma. Again V1 by V2 is compression ratio R. So, this is R power gamma. So, using this relation we can find P2. P2 is equal to P1 into R power gamma. Therefore, P2 is equal to 18.4 bar, 18.4 bar. So, now I have found P2. So, P2 is found, T2 is found, 18.4 bar. So, what we infer is during the process, the pressure during the process 1 to 2 isentropic compression, the pressure has increased from atmospheric pressure 1 bar to 18.4 bar, 18 times, and the temperature has increased from 290 Kelvin to 664 Kelvin, 664 Kelvin. Now, we have found the pressure and this one. Okay. Now, we have found pressure and temperature at state point 2, but volume at 1 and 1, 2 are yet to be determined. If we know volume 1 or volume 2, we can find the other volume, because we know the ratio V1 by V2, which is the compression ratio. So, I will use the basic gas equation of state PV equal to MRT. So, P1 V1 is equal to M, we are taking as 1 kg. So, P1 V1 equal to MRT1, M is equal to 1 kg of working fluid. Therefore, P1 V1 is equal to R into T1. R into T1. So, in this P1 is given in the problem, R is standard value for air, that is characteristic gas constant 287 joule per kg Kelvin, and T1 is given 290 Kelvin. So, here using this one we can find out this one 1 bar. Okay. So, 1 into 10 power 5 into V1 is equal to R is, let me substitute in joules because I am substituting the pressure value in Pascal or Newton per meter square. So, 287 into T1 is 290. So, from this you will get the value of V1. So, V1 is 0.83 meter cube per kg, 0.83 meter cube per kg, 0.0. Actually it should be small v, which refers to the specific volume per unit mass, 0.83 meter cube per kg. Now I know volume at 1, we know the compression ratio V1 by V2, so I can easily find the volume at 2. So, now V1 by V2 is equal to R is equal to 8. Therefore, V1 is 0.83 divided by V2 is equal to 8. So, using this relation we can find V2. Okay. V2 is 0.1. So, after compression the volume gets reduced, the pressure increases, the volume. So, V2 should be less than V1. So, V1 is found to be 0.10 meter cube per kg, which is less than V1. So, for at state point 1, 2 we have found pressure and temperature is given at 1 and at 1, volume has been determined at state point 1, and similar at state point 2 P, V, T, all the properties have been found out. Now, let us go to state point 3, okay. Process 2 to 3, let me quickly go it. Process 2 to 3, this is, what is process 2 to 3? 2 to 3 is heat addition at constant volume. So, Qs is given, so I am going to use that relation. Qs is equal to Cv into delta T is T3 minus T2. Qs is given, T2 we have found, Cv for air we know. So, I can find the maximum temperature in the cycle T3. So, this is using this formula I can find this one. So, Qs is 800 into 10 power 3, Cv is 0.717 into 10 power 3 into T3 minus T2. What is, let me see what is the value of T2. T2 we have found out as 664 Kelvin. So, using this formula we can find T3. So, the value of T3 is 1779, that is 1700 approximately 80 Kelvin, which is the maximum temperature or peak temperature attained in the cycle. So, T3 is equal to 1779.8, 1779.8 Kelvin. So, you can see from the diagram, it is the maximum temperature. So, this is the maximum temperature and this is the maximum pressure. Okay. If you see the PV diagram, 3 is above 2. So, 3 is the maximum pressure. Similarly, temperature 3 is the maximum temperature. Look at the TS diagram. That is primarily due to the end of the combustion process, just before the beginning of power stroke or expansion process. Okay. So, now we have found the temperature at 3. Okay. And what is the volume at 3? Volume at 3 will be equal to volume at 2, because V2 equal to V3, 2 to 3 is constant volume process. Therefore, this is equal to volume at 3, So, this is V2 is equal to V3, So, at 3 we have found volume and temperature. The only thing is we have to find out pressure, the pressure at 3. Okay. The basic equation is apply the equation at state point 2, P2 V2 equal to M is 1 R into T2, P3 V3 is equal to R into T3, divide these two equations, divide these equations. So, P2 by P3 equal to this V2 is V3, V3 by V3 equal to R and R will get cancelled, T2 by T3, V3 and V3 will get cancelled. Therefore, P2 by P3 equal to T2 by T3. Using this relation P2 by P3 equal to T2 by T3, I can find the maximum pressure in the cycle, maximum pressure in the cycle. So, using this formula we can find P3, okay. So, let me underline it, P3. So, using this formula P3, P2 is given, P2 we have found out 18.4 bar, T2 is 664 Kelvin, T3 is this one. So, using this formula if you substitute and find, the maximum pressure will be equal to 48 bar, 48.2 bar to be more specific, 48.2 bar. So, at state point 3 also we have found pressure, temperature and volume. Now, let us go to the process 4 to 1, okay, process 4 to 1. Before that we will find the temperature at 4, consider the process 3 to 4, process 3 to 4. So, once we find the pressure, temperature and volume, add the finding the other quantities like QR, W net, thermal efficiency becomes easier. Process 3 to 4, so write the relation between T3 by T4 which we have used. I am writing the same formula which I used while deriving the thermal efficiency. V4 by V3 whole power gamma minus 1. We know that V4 is V1, V4 is equal to V1 and V3 is equal to V2 because 1 to 4 and 2 to 3 are constant volume process. So, this becomes R power gamma minus 1. Using this formula I can find T4, using this formula I can find T4. So, T4 is 773.8 Kelvin, 773.8 Kelvin, okay. So, T4 is 773.8 Kelvin, okay. Similarly, write the relation between this one for a process 4 to 1, for a process 4 to 1, P4 by T4 equal to, okay, T4. Next, let us find P4. P4 by T4 is equal to P1 by T1, process 4 to 1. This is a constant volume process, this is a constant volume process. So, like this I can write the equation P4 V4 equal to R into T4, P1 V1 equal to R into T1, volume term will get cancelled, R term will get cancelled. So, I will get this equation. So, using this formula T4 is known, P1 is given, T1 is given, I can find P4. I can find P4. So, P4 is 2.7 bar, P4 is 2.7 bar. And what is V4? V4 is equal to V1, V4 is equal to V4 is equal to V1, V4 is equal to V1. So, this is equal to 0.8, already we have found V1 which is 0.83 meter cube per kg, okay. So, now we have found the pressure, volume, temperature at all state points, at all the state points. Now, let us see this one, so that is the first question. Second one is net work output, net work output. The net work output is heat supplied minus heat rejected, heat supplied minus heat rejected, okay. And heat supplied is given in the problem, in the question. So, point part B of the question, W net is equal to Qs minus Qr. This is given as 800 kilojoule minus this is Cv into T4 minus T1. So, when you substitute the values, you will get W net as 453.1 kilojoule per kg, 453.1 kilojoule per kg. And third one is efficiency. There are two ways by which we can find out the efficiency. One is Qs minus Qr divided by Qs, or the formula which we derived 1 minus 1 by R power gamma minus 1. We will get more or less the same answer when we substitute this one. So, the efficiency will be equal to 56.6 which is around 57%. 56.6 percentage. You can use any one of this formula, heat supplied minus heat rejected by heat supplied. And the last one is mean effective pressure, mean effective pressure. So, there is a formula given, net work divided by V1 minus V2, V1 minus V2. So, use this formula W net divided by V1 minus V2. So, you will get 620 kilopascal or 6.2 bar, 620 kilopascal or divided by 100 you will get in bar 6.2 bar. So, this is the mean effective pressure. Okay. So, this is the efficiency. So, to summarize, in lecture number 7 we have seen the first air standard cycle, which is the Otto cycle. Primarily it consists of two isentropic process, that is 1 to 2 is isentropic compression, 2 to 3 is constant volume heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection, constant volume heat rejection. When compared to the actual cycle, the combustion process is replaced by a heat addition process. In case of Otto cycle, it is constant volume. The exhaust process, exhaust stroke is replaced by a heat rejection process, which is again a constant volume process in case of Otto cycle. The working fluid is considered as an ideal gas, which is air. The specific heat remains constant. The working fluid is circulated in all the 4 processes of the cycle. It is a closed cycle, not a open cycle like the conventional petrol engine. With this, I conclude the lecture number 7. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.